Thank you, Dan. So I don't know who I have to blame, but it's my idea of a nightmare to be giving a talk right after Scott Schenker and before Jen Rexford, who you're also going to find out gives spellbinding talks. So you can think of me as the interlude between those two. So how SDN will shape networking, or how will SDN shape networking? Maybe that's what it should have said. So as you heard from Martin and from Scott, a lot of these ideas gelled when Martin was a PhD student here at Stanford, but working with me and Scott when Scott was at Berkeley, and building on lots of work that had been going on in the field. For those of you that are familiar with the 4D work that Jen, who's speaking next, was a part of, and lots of sort of ideas that were heading in this direction. What I want to start with, though, is rather than a research perspective, a little bit of a view of how this is likely to affect the industry as a whole, or what I see as the sort of the industry trend. And in some ways, this industry trend, I think, is bigger than what we're talking about today. It's a much more general trend that's been in motion for a number of years. And then what I want to do is to talk about 4 main points that I think will that will really come out of this, that will shape networking: the empowering of network owners and operators, the increasing the pace of innovation, diversifying the supply chain, and building a robust foundation to networking. But I want to start with this industry change part, and I want to do it by an analogy. And that analogy is to the computer industry of the 1980s. So computer industry in the 1980s meant IBM. And if you were buying a computer, it was based on specialized hardware, specialized operating system, and specialized applications, all from one vendor. It was an industry that was vertically integrated. It was closed, proprietary, relatively slow innovation. But what happened shortly thereafter, and we all know this story very well, along came the microprocessor, an open interface, because it had to be published in order to be able to use it, that led to, over time, many, many operating systems, way beyond the list that I have here. Open interfaces on top of that, over time, led to a very large number of applications. So an industry that was vertically integrated, closed, and proprietary became an industry that was horizontalized, very rapid innovation, and became huge. So clearly, there's something similar going on in networking. It's an industry which has in the past been based primarily on specialized hardware, specialized operating systems, and specialized features and control programs added on top. This was a natural way for that industry to start out. But it's sort of an in transition. And actually, the thing that is driving this much more than SDN as a concept or OpenFlow or anything like that is the availability of merchant switching silicon. And this is really transforming the industry at quite an alarming rate. We're not quite at the point of open interfaces. That's what we're trying to work on here, on having open interfaces to those merchant switching chips. But we believe what will happen on top of that is the emergence of multiple control planes. They may look like things that you see today in the demos. They may look completely different. Only time will tell. Only experience will allow us to tell which ones work and which ones don't work. Some of them will have open interfaces. Some of them will have closed. And eventually, there will be applications and features and control programs that will emerge on top. And so we're seeing an industry which has, again, been vertically integrated, closed, proprietary, relatively slow innovation. We've talked a lot about that today already. Accelerating through horizontalization, open interfaces, and what we hope will be more rapid innovation. And I really believe that software-defined networking, or SDN, is just one manifestation of that, or is one aspect of that. Clearly, what we need is an open interface to the packet forwarding. That's what OpenFlow is, but there could be alternatives, of course. And that we need at least one, hopefully many, network operating systems or control planes. Some will be open, some will be closed, some will be proprietary. Some will have similar interfaces to others, some will be completely different depending on the context in which they operate. We've seen many examples of what this how this might affect us as the owner or operator of a network or as an end user. I just want to offer you a simple example. It's kind of a trivial example, and this is just to take OSPF as an example. So if you take OSPF, and it's not a particularly beautiful method, but it's very, very widely used. It's described in an RFC of 245 pages. And what that 245 pages is describing is the building of a distributed system through the exchange of state to gain a consistent global view of the network. What's the current state of the network? What's the topology? What's the current best view of the topology that it can get? And that's described over about 100 pages. Dijkstra's algorithm, which when we teach about networking and we teach about OSPF, this is all we describe. That's described in 4 pages. And it could easily have been fit into half a page. I teach it in 20 minutes. I'm sure that's how we all learned it in a very, very short description. It's a very, very simple method. So what's the point here? The point here is really one of the most important things that has somehow got lost along the way is that every time that we build a routing protocol, every time we build anything that is a control program or a feature on top of the network, we start by building a distributed system. And we're not very good at it. It takes many, many attempts to do it. And then on top of that, we put whatever the control program is. So if you look inside a router, what do you see? You see an operating system on top of which is a distributed system, on top of which is the protocol that we have on top. And the strange thing is that alongside each of these distributed systems is another one that looks very similar. It's running a different algorithm on top, in this case, in order to pick the shortest path through the network. But this replication comes at a cost. It comes at a cost in terms of just the sheer complexity, the lack of reliability, but it's just inelegant to be repeating this function all the time. So as a simple illustrative example, it's not a particularly beautiful example, but I think it captures something that's going on with software-defined networking. It's not that there's anything particularly new that's happening. It's essentially being refactored. It's being refactored through different abstractions, through different interfaces. And so one distributed system to create that global view upon which these control programs can act. And so it makes it easier to introduce new functionality over time. Because merely all you need to do is to have an understanding of what that distributed system is presenting to you as that global view of the network, and then write that control program to it. Underneath is the interface between the network operating system and the packet forwarding. And the example that we're obviously all talking a lot about here is OpenFlow. I just want to speak for 2 or 3 minutes about this. Scott described it as a forwarding abstraction, and I think it's a very good way of describing it. There could be many possible forwarding abstractions, and I expect over time that others will emerge. But the thing to think about with, or the thing to observe with OpenFlow is primarily it's exploiting flow tables or tables that are already there. So it's timely in that it exploits things that are there. It does not mean that 10 or 15 years down the road, this is the correct way to do it. And I think this is an important thing for us to bear in mind. Standardization has the benefit of giving hardware independence to give a common abstraction. But the thing that we should be focusing on is the standardization in a pragmatic way. Perfection is not the goal here. A good enough abstraction is what we need. So what is it doing? It's exploiting this flow table and then populating that flow table with rules of the following sort. If you see a header that looks like this, it has a header of P, send to port 4. If you see a header of Q, overwrite some fields and send a collection of ports for multicast or for multipath. If you see an unknown header, perhaps send it to me or drop the packet under the control of the network operating system. What it's really doing is providing a match plus action, and I think this is actually the key. The precise details of the mechanism matter less than this general abstraction of forwarding into, if you see something that matches and looks like this, then you perform an action. But actually, this is just an abstraction of how every forwarding element works in the network today, whether it's layer 2, layer 3, it's an ACL, firewall, etc. All of these boxes are doing a match plus an action. And OpenFlow is just one example of how you could do that. So basically, you match on a selection of, on a set of rules that define a header. You would like this to be as general as possible to match on any header that you can define, or a new header that you create that's specific to your network. And then you pick the granularity depending on where you are in the network. If you're towards the edge, perhaps you want to find granularity, and then aggregate as you go towards the middle, as we do today, but perhaps in a way that fits your context. It may be VLANs, it may be MPLS, or something that's created locally. And then the actions, in the case of OpenFlow, that set of actions is designed to be very small. Things like, if you match, then forward to a port or a set of ports, drop the packet, send to the control plane. Overwrite the header with a mask, in other words, modify or overwrite the fields in the header. Push a new one on in order to be able to create encapsulation or pop to decapsulate, and forward at a specific bit rate. Really, the particular challenge that OpenFlow faces is not really on this whole match mechanism, it's on this action mechanism. And that is, how do you use the minimal set of actions to be a meaningful set of primitives from which you can do most things that you want to do, while leaving room for chip vendors to be able to implement in hardware, and box vendors to differentiate by adding additional features and additional capabilities. And so it's been a crafting of trying to figure these out as we go. And I encourage and implore all of you to help in that process. You will look at this and say, there are things that are missing. Well, then think about, well, maybe I can add that in my box and differentiate from everybody else. Maybe that there are things that you think should be there down the road. Well, get involved in the ONF and working groups and help steer it in that direction. Because as Martin said very eloquently, in the end, this is what we make of it. And we, as everybody in this room, represents a large fraction of the networking industry. And in order to make this better and to improve this, we all need to take part in moving this along. So in the end, what the abstraction that it provides us is protocol independence, because you can potentially, not right now today, but potentially in future, construct a variety of existing protocols, construct new forwarding methods, yet in a manner that is backward compatible and that you can stick it into an existing network and have a box that looks like a BGP router or an existing firewall, and then have that as a point of innovation so that you can improve that over time. And that it's largely technology independent in that there are flavors of this that have been added to switches, routers, Wi-Fi access points, cellular base stations, even WDM and TDM circuit switches, because that flow abstraction works equally well in that context. And so as a consequence, many people have chosen to develop products around this in domains that I've listed here. I'm sure there are others that I'm not aware of: data centers and public clouds, enterprise and campus networks, cellular backhaul, enterprise Wi-Fi, WANs, home networks, and the number of switches and routers and software vendors and startups. This is a great area to be looking for a job right now. The most common email that I get at the moment is, how can I find somebody who can work in this area, because I'm expanding in networking for the first time in 5 or 6 years. But how will this shape networking? How will this shape how we use the network? Well, for this, I want to go through these 4 points in turn. And I'm going to use this as an opportunity to illustrate some of them with 2 or 3 examples, and these are research examples, just to give a sense of the things that we might be able to do as a consequence of SDN. So the first one is the ability to empower network owners and operators. We can already see when network administrators here on campus and in other university campuses that have been deploying OpenFlow and SDN networks, that once they have the ability to customize that network for their local needs, that's what they do. They start to come up with features and capabilities that they'd like to put into their network, which is something that they've not been able to do in the past. And in fact, there's a wonderful opportunity here for a growing sort of peer group amongst people who already know each other and work with each other across universities, between universities, across the country and across the world, to be able to develop ideas, exchange them, and to gain status within that peer group, just as people do within the software industry as a whole. But more broadly, people will customize their networks not necessarily by programming it for themselves, but by paying others to develop features and capabilities for their network through a new set of suppliers, through a whole new part of the industry. Others will use this as an opportunity to eliminate unneeded features. If you have a router in your network today, it has somehow had to address about 6,000 RFCs. And so that router is extremely complex, and we know how reliable they are. Given the opportunity to be able to eliminate the 99% of those features that you don't actually use in your network, gives you a potential to make it more reliable. And so some people will choose to do that, not all. So that will be something that others choose to do. Some of the networks that are being built right now are being built for very specialized applications using this technology because they only need 3 or 4 features because they don't have to carry the legacy of 1,000 different types of user. Others will use it as a tool for building virtual networks which isolate sets of users, perhaps in multi-tenancy, or in just as a means of dividing up sets of users as we use VLANs today. Many ways to use this in order to be able to isolate networks which have particular performance guarantees. It will also have the effect of increasing the pace of innovation. Once you can define the operation in software, then we move into a completely different culture, as Scott was alluding to earlier. Innovation will start to happen at software speed. Standards, if there are any, it remains to be seen what standards mean in this environment, will follow the software deployment. In other words, rather than today, where a number of people sit in a room, define a new feature or a new capability of a network, and then we all wait for 5 or 10 years for that to become available, we will see deployments that people use, that they share with others, that they gain experience, and then somewhere afterwards it gets solidified and gets standardized, maybe, if that's helpful for the further deployment through the industry. Others will just choose, for example, to peer with their neighbors using things that they've cooked up between them. So you can imagine one provider peering with another and saying, well, across our boundary, we'll actually use something that we've found works better for us. And then at our combined boundary, we'll peer using BGP or whatever happens to be used. And so over time, you might imagine islands growing up of techniques, whether it's routing protocols or whatever it happens to be, that support the particular needs of that part of the industry. So the consequence of this will be some amount of chaos, a need for a lot of diligence in testing and of communication. But on the other hand, we can expect to see a much more rapid pace of innovation. And we like it in the university, and there are a number of researchers here. We like it because of the ability to try out ideas, and for the first time, perhaps ever in networking, to be able to influence industry by transferring good ideas, if we have them, right? By taking ideas and being able to, using either networks of our own creation or of programmable testbeds like the Genie testbed being funded by the National Science Foundation, in order to be able to try out those ideas, experiment with them at scale, show our peers, show industry, and then if those ideas are good, for those to be transferred and then more widely adopted. So I want to pick out 2 or 3 examples here. So how might I customize my network? And I would just want to use an example of someone here, a student who's sitting at the back of the room, Nikhil, who was interested in customizing a network that we had here on campus, and then extend that idea and to be able to demonstrate it over a much larger scale. So his idea was to add distributed load balancing to the network that was here, and then more broadly across the network interconnecting a number of campuses. So we all know what load balancing is. Load balancing is when a set of requests, in this case, number of HTTP requests, are delivered across a network to a randomly selected server or to one that's lightly loaded. Ideally, That request would be sent over a path which is lightly loaded to a server which is lightly loaded. In other words, we would jointly optimize the combination of the path and the server in order to be able to minimize the request. Today, in order to do that, we have to go and buy several $100,000 boxes and place them in the middle of the network, and yet all they can do is pick the server, they can't pick the path. So even though they sit in the infrastructure, they're part of the network, they're unable to choose the path. They have to use the path that's handed to them by the network. So he was interested in the question, what if you could jointly optimize that path and server and see whether you actually got a better response? And he wanted to do it in networks that look like this. Campus networks interconnected over a backbone where the requests could come in from any direction, so there was not an obvious place to put the load balancers. So in this particular case, the load balancing was to be distributed through the entire network, so that every switch was capable of load balancing just because of a omniscient control plane that would see the requests that were coming in and be able to route to the servers as needed. So the experimental setup looked like this. A network operating system, in this case Nox. It's an open source control plane originally created by Martin, and then wrote this as a control program on top, and then deployed it into the Genie network, which at the time looked like this: National Lambda Rail and Internet 2 networks interconnecting a number of campuses and BBN across the country. So I'm going to show you a demo that we showed about a year ago at a Genie conference of exactly this. This is of a number of clients at the edge sending requests to a number of servers, which are shown around the top right-hand side. The numbers just show the response time for the servers. So these are HTTP requests being randomly sent to these servers without any consideration for the network. As you might expect, the network becomes very congested in some places, and so the average response time is all over the place. So this is the average response time seen by the client of that HTTP request. So highly variable, not something that you would like to see. Now, we're going to more smartly load balance by every time there's a request, pick the path and the server jointly in order to minimize the expected response time. Choose the path using that control plane, pushing that down into the switches. And it's not going to use a particularly clever algorithm. It's just going to greedily pick the one that it's been the most likely congested in the near past. And as you can see, and this was done from a live demonstration, so these numbers were being measured at the time. It moves from the red line to the green line. There's a dramatic reduction not only in the response time, but also in the variability. My point here is not to say that this is the best way to do it, that this is going to be widely deployed in your network anytime soon, or that you couldn't improve upon it with spending a little bit of time on it. The point here is that for the first time that I have ever seen, a graduate student was able to take an idea and within a few weeks put that into a national network, run real traffic over it, was able to demonstrate it to others, and then hand it to them and said, here's the code. You can actually go and run this in your network too, and you can use that as a basis for improvement. And so that's what this software-defined networking and a testbed like Genie made possible. So in this particular case, this entire code, in order to be able to do this as a feature added on top, was actually less than 500 lines of code. So we've seen this time and time again, that by placing this kind of facility into the hands of students, and I think that in future we'll see this putting into the hands of engineers, both engineers developing the infrastructure and people owning and operating the network, that they too will have ideas that they will want to put into the network. And we've started to see this happen already. There are a lot more videos that we've created and others have created of demos at this particular location. And so if, I'd encourage you to go take a look. So on this second point of increasing the pace of innovation and innovating at software speed, I want to offer you another example that some of you saw yesterday as another way in order to be able to innovate that's provided by SDN. And it comes as a rather subtle consequence of this. That once you have a well-standardized, well-defined interface to the hardware, if that is a narrow interface, then you can start to emulate that and create entire testing environments that instead of needing a big test lab and spending millions of dollars on it, you can start to do much of that testing in software. And we've seen some large companies already beginning to do this. Because it's impractical to take commercial switches and routers and to be able to emulate a whole network made from them. But if the interface that they provide is fairly narrow and fairly simple, you only need to emulate that. An example of this is the Mininet system that many of you will have used in the tutorial yesterday as a means for rapid prototyping. So I just want to tell you briefly how this works. Basic idea is this. So we're going to take the example that I just showed you of that network with the operating system and the load balancer sitting on top. And then we're going to map this into an emulation. And we're going to include some end hosts that are going to be generating some traffic as well. And we're going to put this onto a server. This is the server at the top here with the user space and the kernel space. And we're going to take the packet forwarding pieces, put those into the kernel of this machine, take the various processes and put them into processes on this machine, including the end hosts. The thing that makes this possible is, for those of you familiar with these things, is the network namespace addition to Linux. It's been a number of operating systems that allows you to do lightweight emulation by taking, it's a little bit like lightweight virtualization, where you can take a process with its own network namespace as you would expect to see for a virtual machine, and then be able to run that at much, much lower overhead than it would be for a full virtual machine. And then you stitch these together with virtual Ethernet interfaces. One of the cool things that you can do is then take any of these pieces and then move them over cores or even move them over machines, and start to then emulate at really quite surprising speeds. So why does this matter? Well, it matters because it's fast. You find that you can emulate quite nicely networks with tens of switches just on a single laptop, as many of you saw yesterday. By mapping these onto cores and servers, you can emulate networks with thousands of switches just on a server rack. So instead of needing millions of dollars of equipment in the lab, you can potentially try out new versions of software, new versions of control programs, new ideas in this environment first, and then you rapidly transfer it into the network. So we've done a number of demonstrations where you can deploy that unmodified code without change from that Mininet environment directly into the live network, and in some cases even into a slice of that network without ever taking the network down. So you get much, much more rapid pace of innovation as a consequence of this. And for those of you who want the code, it's available there. So getting back to this, how will SDN shape networking? It will also diversify the supply chain. We've already started to see a variety of software suppliers step forward. I think we've only seen the beginning of this. There will be many more existing vendors. The best placed companies to innovate in this area are going to be the existing vendors who have the most experience. But there will be startups, of course, that come along and compete with them. We'll see vendors, a much greater variety of vendors. People will do homegrown. They will outsource to others. They will ask consulting companies to develop new features for the network. We'll see open source. We'll see all of the above. And last, I think it will build us a robust foundation in the spirit of what Scott was describing. The turning something which is the mastering of complexity, something which is something of an ad hoc discipline, into something with much greater precision and built on a much stronger foundation. So the standardizing the forwarding abstraction is just one part of that. But as those abstractions become nailed down on top, and we begin to think in terms of this abstraction of networking control, we will start to have provable properties at each layer of the network. And I just want to offer you one example here of, again, some work that we've been doing here on provable networking properties at the lowest level. And I think that this will be, we will see similar examples like this operating at other layers of the control plane as well. This is something that Payman, who's sitting at the back, has been working on something called header space analysis. So I view this because it's not about an application, it's not about software, it's about what this basic model allows you to do, and I think it will give you a sense of some of the other things that will become possible down the road. So in this particular case, we're going to use the fact that the lowest portion of the network is this match plus action primitive in order to prove properties of the network and do some static checks of questions that have been very difficult to answer in the past. So in today's networks, some very simple questions are really quite hard. Things like, can A talk to B? Is there any type of packet that A can send that can reach B? Or what are all the packet headers that A could send that would reach B? Can you describe those to me? Even if the network is transforming those packets as they go through. They're very hard to answer. But if you're trying to debug a network and understand its operation, then these kinds of questions are very important in order to be able to work correctly. Are there any loops in my network? Is one VLAN actually isolated from another? Are there ways in which information can leak from one to another? Or if it's a slice, can information leak from one to another? This is important, obviously, in an engineering environment, but in a hospital and for things like HIPAA compliance and PCI, this is extremely important. So the approach that the payment has taken is, first of all, to map the entire set of headers, this match plus action primitive, model the entire packet header as just a single point in a space which is L-dimensional, where L is the length of the header. You'll see in a minute that you've all seen this before. What I'm describing is digital design, but bear with me and you'll see that in a moment. So we're going to map it as this single point, and then we're going to model all switches as transforming this space. All switches, routers, firewalls, everything is going to transform this space. And then we're going to analyze reachability based on those transfer functions. And it's all building on this match plus action. And we'll see that because of this, it's protocol independent, it's very general and quite surprisingly fast. So let me explain a little bit more. Take a packet header, L bits of the header, whether that's L2, L3, L4, or 1,000 bits, that's irrelevant here. This space down here is the L dimensions. I can only really draw 2. I've attempted to draw 3. I certainly couldn't get beyond that. Dimensions here, for which that header represents a single point. It's a specified point within that space. Now, a rule that sits in a flow table, whether that's an L2 table, an L3 table, or an OpenFlow table, will be represented something like this. If you see something that matches these bits with these wildcards, then I want you to perform some action. Well, that represents a region within that space. What does a packet forwarding element do? Whether it's a switch, a router, a firewall, doesn't really matter. It's going to transform that space by performing actions when it sees matches. So if it was to send to port 1, it might transform that space to something that looks like this. It might be modifying the header because it's a NAT. It may be unmodified, as in layer 2. Doesn't matter, it's going to move or transform that in some form or other. And so we can map the transfer and the operations that are performed on this space. If this is reminding you of Carnot maps and Boolean algebra and logic minimization, it's a lot of similarity. And in fact, there's a whole algebra that you can build up from this that allows you to perform these analyses that are exploiting the fact that underneath, you've just got this match plus action primitive. And so from this, we can build an entire network transfer function. What is the transfer function of the entire network? So if I put in packets that look like this at one end, what will pop out at the other? And then you can ask of that things like reachability analysis, ask it to detect loops that are finite or infinite. Where is this coming from? This is coming from because of this network transfer function that sits at the bottom, and it's just a bunch of Boolean expressions. So then you can throw all of the machinery that was developed for CAD and formal verification at this, and even use model checking in order to be able to answer some of these questions. Only relies on this match plus action, so it subsumes the things that we already use without being dependent on them. And then you can use it to find faults in real networks. So Payman took this, he took all the configuration of Stanford's backbone network, parsed it to create the transfer functions, and then was able to say, who can talk to whom? Where are the loops? And found a number of sort of surprising things. And was able to do that in about 10 minutes. So again, please contact us if you're interested in exploiting some of this. So the point that I want to make here is not that any of these 3 particular examples are things that you should run off and use. They may or may not be of interest to you. But what software-defined networking does, and what it will do to the industry as a whole, is introduce new ways to make the foundation stronger, to allow us to innovate faster, to allow us to innovate on our own. And as a consequence, the entire industry, I think, is going to change. Thank you.